This is the video showing question 2 of the work set last week for 11HT. Question 2a. A company is developing a system which can heat up and melt ice on roads in winter. I'm going to allow you to read the rest of the question. The key idea here is that the road surface is black and we need to suggest a reason for why this is the case. I've put 3 links in here so you can revise this if it is unfamiliar with you or you have forgotten it. The first link links to the BBC Bitesize, the second one to the work in Seneca, and the third link to a practical called the Leslie Cube, which we will go on to look at later on in the course. So why is the road surface black? Black is a good absorber of infrared radiation. That's the mark for 1 mark. So if we look at this question here, what is meant by specific latent heat of fusion? This work was covered in year 9, but just to remind you, this is when we have a change of state happening. And when a change of state happens, instead of energy going to raising the temperature of the substance that's being heated by increasing its kinetic energy, it's actually breaking the bonds so that we're getting a change of state. So the definition there is the amount of energy required to change the state of a substance from solid to liquid with no change in temperature. And when we're looking at latent heat of fusion, it's melting a solid or freezing a liquid. If we're looking at the latent heat of vaporization, it's the amount of energy required to boil or to condense a substance. So again, a couple of links there for you to support you in your learning. Part 2 asks us to calculate the amount of energy required to melt 15 kilograms of ice at 0 degrees Celsius. The specific latent heat of fusion of ice is 3.4 times 10 to the 5 joules per kilogram. So it's important that we understand the formula for this. So a change in thermal energy is equal to the mass times the specific latent heat. So the temperature really not playing a part there, it's a distractor. So if we look here, delta ET for a change in thermal temperature, we've got our mass and our specific latent heat. And you can see the units up there for you. So let's have a go. Pause the video, have a go. Now you have the equation and restart in a second. So we can see here, here's our formula. We insert our values in there, 15 kilograms in the right units, 3.4 times 10 to the 5 joules per kilogram in the right units. Times those together, we get 5,100,000 joules, or 5.1 times 10 to the 6 joules. 1 mark for substituting in the values and 1 mark for getting the correct answer at the end. Remember the units always. Right, part C. Information here about melting ice, and an investigation of melting ice varies with the mass of salt added. So state 1 variable which the student should have controlled. The student should have controlled the amount of ice in the beaker, or the mass of the ice in the beaker. So volume, weight, amount, or quantity of ice would all get you 1 mark for this question. During the investigation, students stirred the crushed ice. 2 reasons why this is the case. Well, the first 2 hopefully are fairly clear that they're not the correct answer. Reduce energy transfer from the surroundings to the ice. Interesting. So that leaves us with 2, ensuring the distribution of the salt and to make sure that the ice is all at the same temperature. Part 3, we're looking at this table of data, and we can see that we've got a relationship going on here. As the mass of the salt added increases, the melting point of the ice decreases. So that's the pattern that we're looking for there. So the melting point decreases as the mass, or you could say concentration of the salt, increases. So negative correlation would get a mark there if you explain it in terms of relating that to the melting point or the concentration of salt, but it is not a inverse proportion relationship.